Hey, hi everyone. I am so excited to chat with you today about our evolving data transfer protocols in Filecoin and IPFS, and how we're going to make the distributed web more reliable, accessible, and interoperable. So my name's Hannah. I am a programmer with the Web3 Data Systems team at Protocol Labs. I've been working on IPFS and Filecoin for about 3 years, and honestly, in my entire career, I have never worked on more fascinating technological problems than I do now. And I hope by the end of this talk, you are as interested by them as I am. Bailey, if you like the first slide, there is a lot more David Bowie coming because my Filecoin orbit theme fell to earth and it's full of space oddities. So let's go ahead and get started. I want to start with a very simple question. Do you trust the data that you download on the web? When you enter a value in your web browser, how do you know the content that you were looking for is actually what you got? And the surprising answer is you don't really know. In the traditional web, if the website uses SSL, you have some guarantee that you're downloading from the right site, but you still don't know if you're downloading the right data because you don't know if that site's been hacked. Plus, SSL is like pretty cumbersome to set up and maintain for people who are running websites. And while there are, in fact, ways to check your data, they're so cumbersome that only the most technical people use them. So it's somewhat surprising that the whole web works at all. But in the distributed web, we want to do better, right? And that's what I think is one of the most core innovations of IPFS and Filecoin. We've developed data formats and addressing schemes that provide much better guarantees about the data you download. Trusting data is no longer about who you get it from, but rather whether it matches a cryptographic contract that's built into the address that you use to find it. Put simply, you cannot download something you did not ask for. So let's talk briefly about our data formats and what they enable us to do. The first thing I want to talk about is a content identifier, or CID. It is a way to identify content that is cryptographically secure. Inside of a content identifier is a cryptographic hash of the types of the block of bytes that you're going to download. And a CID also contains information about how data was encoded to help us interpret those bytes at a higher level. As a quick aside, CID is sometimes pronounced just SID, and I'm going to try not to do that. That's sort of an internal shorthand we do. But if I do, that's what I mean. But I'm going to try to say CID. So most blocks of bytes on our network decode into a structured data format called IPLD, or interplanetary linked data. This means that you can take the bytes you get for a block and decode them into something much more meaningful. And the data model of IPLD is similar to JSON in that it has basic data types like strings and numbers and collections like lists and maps. However, IPLD also supports embedding content identifiers into that structured data, and that allows us to break up large data sets over lots and lots of blocks. In the sort of contrived example you see on the screen, we have a list, and it has 2 maps inside of it, and the first number is a CID, and in the first map there's a CID that links to an image, I'm going to call this cheese image, and then there's a string value, and then in the second map you've got there's a number value, and the second map has a CID that links to further data, as well as a string value with the name of the fruit in this case. The linking in IPLD is in a lot of ways very similar to HTML. It is almost a hypertext format, but it's structured data that a computer can understand. And the links are CIDs that will guarantee we get the right data. So fun fact, almost all data that is stored in Filecoin is encoded in IPLD. When you make deals in Filecoin, you probably make them for files or directories, but all of those are encoded to IPLD formats before they get transferred. And that produces some unique advantages that we're going to see in just a moment. Large data So that's our format. And then large data sets in IPLD can get spread out over multiple blocks, where each block is identified by its own CID and embedded into the IPLD data for that block are links to other blocks, all going back to an individual root block. We call this a Merkle DAG. The awesome thing about this is while the root CID is just a hash of the initial blocks in the first root block, you can use it to incrementally verify the entire graph. Once you find and verify the first block, you can go, you have CIDs for the next blocks, and you can go find them and verify them until you can keep going until you know the whole graph is cryptographically the data you wanted. And we've even written a query language for IPLD called selectors. And selectors allow you to describe partial traversals of IPLD data sets. So if you encode, for example, a large data directory tree in IPLD, we have a way to describe a path from the root to that whole subdirectory deeply nested that can be cryptographically verified. There's a lot of benefits that emerge from these core data formats. Using CIDs means you never get the data. You never get data you didn't ask for. We've talked about that already. And since you can verify data, you can verify the integrity of data, it doesn't matter where you get it from because you know it's the right data. IPLD formats allow us to break up large structured data sets into incrementally verifiable chunks. And that means we can get data faster, but we can ask lots of people for smaller parts of the whole. And plus we never need to, if we have a single chunk that appears twice in a graph, we only need to send it once. Finally, we are starting to see the building blocks here for trustless payments for data. If I can verify data incrementally, I can break large transfers into much smaller transactions, minimizing risk on both sides for a paid transfer. So let's talk about the technologies we built for moving all this data around. One of my favorite parts about working on IPFS and Filecoin is that you almost get to start over and work on and try to write the core protocols that power the web and do it better. It's like programming in the 90s and you're trying to figure out how to implement HTTP or early file sharing protocols like Napster, but do it better. So the first distributed protocol we implemented for IPFS was Bitswap. And Bitswap is a block exchange protocol. It doesn't actually understand anything about IPLD. What you can do is you can ask for a CID and get a block from a peer and get a block back. It's kind of like BitTorrent in that sense. You ask peers for individual parts of a larger data set and then assemble them yourself. The IPLD knowledge here lives entirely outside of Bitswap. Usually it's on the client who's requesting data. This has some really great advantages, and that's why Bitswap remains the core transfer protocol in IPFS today. There's some great things about working at the block level only. First, since you're only asking for one block at once, it's really obvious how to break up requests among many peers. You just ask different peers for different blocks. And since you're breaking up requests, it's easy to make them in parallel. And plus, because the person who's sending data in response to a request is only sending block data, they're only sending bytes, they don't have to understand the format that those bytes are encoded in. They don't need to know anything about IPLD. Plus, Bitswap is a really mature protocol. We've worked on it a while, and the Go implementation is pretty efficient, and it does a whole lot. There are some challenges, though. Bitswap, because you only ask for one block at a time, there's certain types of nested traversals, like fetching a subdirectory deep in a graph in a nested directory, where that produce lots of round trips to get the data, because you don't know what the CIDs farther into the graph are. You have to ask for the first, and then the second, and then the third, and then the fourth, all the way to get to your end. And that's pretty inefficient. Also, Bitswap, for people sending data, since you're only getting very small requests, it's pretty hard to optimize your disk I/O and your network I/O so you can send lots of data at once. Finally, the block level nature of Bitswap does tend to produce a lot of network traffic, similar to the traffic congestion problems that you see in BitTorrent. And this has resulted in, and the other part is not a problem with Bitswap itself, but the implementation of Bitswap that we've written for IPFS, the Go version, has kept growing and growing and growing. So it's way more than a protocol implementation. It's almost an entire data transfer stack. And it's so tightly integrated with Go IPFS that it's almost impossible to pull them apart. So it's not surprising we ended up writing a second transport in the context of building an entirely new technology with Filecoin. So the new transport is called GraphSync. It's kind of our new hotness, and it powers all of the data transfer in Filecoin. And GraphSync is a protocol for replicating entire IPLD graphs across peers. Rather than request a single block, in GraphSync, we request a SID and a SID selector. And that allows the peer to stream us all the blocks that match that query. In essence, we're performing an entire query against a remote IPLD data set. And we can ask for and receive much more data at once. We developed GraphSync because we knew that for storage and retrieval deals, we would require fast point-to-point transfers between clients and miners, similar to HTTP. And GraphSync, because the person sending data processes much higher level requests, they can read and marshal their data ahead of time and send it over the wire. So there's no extra round trips, and we should be able to max out to the speed of the network pipe. And since we started from scratch, GraphSync is a lot more configurable than Bitswap. We support custom authentication, sending side channel information like payments, and distributing individual requests to different data stores. On the receiving side, a lot of these things are easier to deal with when you're dealing with higher level requests. And this configurability has enabled some of the really cool optimizations that we're starting to see in Filecoin that you may have heard about, like the DAG store. It's allowing us to do IO at much faster speeds. And we're starting to support really large storage clients like Estuary that are sending out tons of data at once. And that kind of scalability is just really hard to do with Bitswap. But GraphSync has its own challenges. First, because you're dealing with large requests, it's harder to break them up. It's not always clear how to break up a selector among peers. And second, we want to maintain our guarantees around incremental verifiability, and that turns out to be fairly complicated. So our implementation is complicated. The other challenge with GraphSync is that you need a greater shared understanding on both sides of the network transport. Because the responder is essentially doing an IPLD selector query, they have to be able to execute it locally to get all the data. And this gets complicated because IPLD is pretty extensible and supports a number of customizations. And finally, again, this isn't a problem of GraphSync, but Go Bitswap does so much. And it's so much more than a transport protocol. So when you start a new protocol, you don't have all that, and it's just missing. So we've got some challenges. And probably our most obvious challenge that you may have been apparent up till now is that we have two different stacks. We have a transport stack for IPFS and a transport stack for Filecoin. And it's not just Bitswap and GraphSync. It's all the services that we built on top of them. In Bitswap, we have Bitswap Sessions, which is sort of an optimization protocol for doing higher level transfers. And then we have services like the block service and DAG service that are baked on top of Bitswap and hard-coded into that. In Filecoin, we have GraphSync, and then we built other components on top of it to support Filecoin's needs. We have a control protocol called the data transfer protocol. We have a Filecoin retrieval protocol and a storage protocol. And finally, we have this support for payment channels so that we do, in fact, support paid transfers in Filecoin. But the larger problem is that data retrieval is about so much more than transport protocols. To build interoperable solutions, we need to think holistically about what the data transfer process looks like, so you can download any content for any protocol from any peer. And so we've started to do that, and we've identified 3 high-level steps in the data retrieval process. The first step is content routing. This is essentially finding your content. In the regular web, you ask users to know website names, and then you use DNS to find those websites. In the distributed web, we just start with a content identifier that could be hosted anywhere. And we need to track down who has that content and how they're making it available. We've developed, again, different solutions here. With IPFS, we have the DHT, or distributed hash table, which enables us to find any content on IPFS, even though it's sometimes not as fast as we'd like it to be. We also have a Bitswap want protocol that enables speeding things up among local peers, because you can ask them whether they have a block without them actually sending it to you. On the Filecoin side, it's really still early days. Will Scott gave a talk earlier today about the indexing solutions we're building to help people find content on Filecoin, but a lot of it is still in development. Once you've found content, it's actually not an immediate step to making a transfer. We need to plan the best way to get it from potentially multiple sources. And there are a lot of factors we need to think about. We want to get it fast, and we know we probably want to get it free or low cost. But that might mean we're distributing the requests over many peers or switching between protocols or making trade-offs to maybe pay to get things faster. Plus, we have to recover from failures if peers turn out to not have content. Concretely, almost none of this exists for Filecoin content today. It's largely manual. And we do have a lot of planning in IPFS in Bitswap. That's what the Bitswap sessions largely do. It's really great. It just only works for Bitswap. Finally, we have what I've already been talking about, which is transport. How do you get things from one place to another? And here we have really great protocols, but there's one thing missing. And that's accessing all of the Web 2 data. Right now, to use our protocols, you have to run an entire libp2p stack. What if we could bring some benefits like content and identifiers and incremental verifiability to data that's available only on the traditional web? So I want to talk to you briefly about how we're going to figure this out going forward. We know we want people to be able to download IPLD content from IPFS, Filecoin, and even maybe HTTP as fast as possible without having to think about where it's coming from or what protocols it's sent by. Wow, that's a tall order when you say it all together. Well, the good news is we've begun work on a prototype client that can retrieve data from IPFS and Filecoin, automatically choosing the best way to get it. So that's really good news. So how are we going to do this? The first thing we're going to do is we're really going to cleanly separate the stages of data retrieval I've been talking about. While all of these steps are asynchronous, they are distinct. We want to separate finding content, planning requests, and executing transfers. Now, it's not entirely that simple because feedback goes both ways in a large transfer request. We still want to be able to swap, but we still want to be able to swap different solutions at each step. What we're thinking about content routing now? It's a problem of finding content from multiple sources. Some of them are fast, but have very little content, like a local data store or local peers. And some of them are very slow, like the IPFS DHT, but have tons of content. We already actually do this without thinking about this in our IPFS stack, but we know there's going to be more sources over time. So we need to build a framework for fetching from multiple sources. And honestly, we know other people might build better solutions for finding content. So soon you're going to see delegated content routing coming to IPFS. And in our new retrieval stack, we want to allow people to plug in their own solutions at each level. The fastest way to get to an awesome retrieval client that downloads fast from anywhere is to provide a framework in which people can discover and implement the best-in-class solutions for individual parts of the problem. Solving planning is not obvious. The planning stage is going to be a complicated one. It's not easy to mix protocols and peers and payments and always deliver the optimized solution. We have some thoughts, but they're just preliminary. For Bitswap and GraphSync, we think we can mix them and get the best of both worlds. GraphSync helps us understand whole graphs and get them in a single round trip, but Bitswap is good at splitting requests. So what if we use GraphSync to get a description of the graph in terms of SIDs and Bitswap to actually fetch it? This is just one of the proposals for how we could get the best strengths for each protocol. And we're just going to have to evolve solutions over time. One other thing we are definitely considering is HTTP, and we've developed a proposal for incrementally verifiable transport over just HTTP 1.1. So when is all this coming? I don't know, 2022? This is not a product announcement. This is not your FBM keynote. So we'll hope it's going to be very soon, but it'll be even faster if you help out. So thank you very much, and beware of the spiders from Mars. Thanks.